Good morning, students. Today will be the last lecture of gas absorption and stripping. So, in last lecture, or instead of last few lectures, we understand how to calculate the height of a packed bed. So, there is numerical method, and then there is some simplified method or analytical method for dilute solution case. Okay, and we have solve few problems on this. Today what we will see the how to determine the number of stages in a plate column or tray tower. We know that for a plate column the plate spacing will be between 1 feet to 3 feet depending on the flow rate, and also we know how to determine the diameter of the column, that is from the chapter 5. Now if today we will calculate how to determine the number of ideal stages. So if number of stages is 10, then if tray spacing between two tray spacing is 1 meter, the 10 into 1, that will be 10 meter will be height. And so let's see how to calculate the number of ideal stages. So if you want to calculate the number of ideal stages for a plate column or tray column or a tray tower, from the problem statement you can determine the minimum liquid flow rate for absorption, and you can calculate the minimum gas flow rate for stripping. That already we discussed in the beginning of this chapter. That is the common. So once I calculate the minimum gas flow rate or minimum liquid flow rate for a particular system, then from then I can calculate the operating liquid flow rate or operating gas flow rate, and that will be generally 1.222 times of the minimum liquid flow rate or gas flow rate. So once we will get the for absorption gas flow rate will be given, so I will calculate the liquid flow rate LS, so then I can get the slope of operating line LS by GS. And for stripping, liquid flow rate will be given. I will calculate the minimum gas flow rate, and from then I can calculate the actual gas flow rate. Then also I can calculate the slope of the operating line. So I will get this LS by GS. So once I get the operating line and there is equilibrium line, then we will draw the triangles what we discussed in the chapter 4. So I will draw the triangles, and from there we will calculate the number of ideal stages. I can do it either graphically or numerically using Krebs equation. Already what we have discussed in chapter 4, that will determine. Okay, only thing we have to do here, I have to calculate the liquid flow rate and gas flow rate for this problem from the minimum flow rates. That thing we have to add, then I will go this chapter 4. That's why I told repeatedly, when you learn in chapter 4, that is the basic. See, this is nothing, just we are using this one. Okay. So this way you can calculate this number of stages. Okay, number of ideal stages I can calculate, and then from this what will be tray spacing, that will be of mine. I can hide the diameter of this thing. Okay. Now another thing important term is in here, height equivalent to theoretical plate. height equivalent to theoretical plate. Means what is the spacing between these two trays? What is the height? Okay, so it can be done like this. So if I know that height of the column and height of the column, I will calculate from the pack tower. The pack tower and plate tower are two common devices for absorption of a solute gas from a mixture. In the former device is selected, the packed height is to be determined. In the case of plate number of plates to be found out of given separation job. So factor your height, the packing height, and number of trays, and that will be height of a height equivalent to theoretical. And from this calculation, also it has been seen that height of a equivalent theoretical plate, it is between 1 feet to 3 feet, means 0.3 meter to 1 meter. So that's why if you see practical, I told that tray spacing is between 0.3 to 1 meter, and that also if the people did this calculation, it came like this. Okay, so this, and there is a relation. I am not going to so many things. So there is a relation to height equivalent to theoretical plate equal to HTOG ln mg dash by ls. Mg dash ls means h2og ln s bar by 1. So this relation is there, height equivalent to this. So if you calculate the pack tower height, this, and with this equation you can calculate the height of a height equivalent to theoretical plate. Okay. So, and whatever this derivation is given here, but it is not required, but you should have some conceptual thing that what is height equivalent to theoretical plate. Okay, now last thing of this chapter is tray efficiency. So I told that tray efficiency would be 100% when for a particular tray what is leaving gas flow, what gas is leaving from this tray, and what is liquid is leaving from the tray, means yn. For nth tray, yn and xn, if they are in equilibrium, then tray efficiency 100%. But to bring this gas liquid mixture in equilibrium means it takes much time, but practically it will not reach to the equilibrium. Generally it will be near to 60% of this equilibrium value, or 40%. This is a very common value. So accordingly, that's mean whatever ideal tray we are calculating from this thing, let's say from this calculation I am calculating the ideal number of trays. So I am making triangle means when I am touching the equilibrium curve means it is in 100% efficient. But means xy is in equilibrium, but practically it is not like. So let's take, I have calculated the number of trays equal to number of trays equal to, let's take 10 number of ideal trays. Now if tray efficiency is 60, let's take 50%, okay, then 50%, then actual tray will be 10 by 0.5 means 20 number of trays, because whatever we have calculated, that based on that trays are ideal 100%, but practically it will be less. Okay, practically let's take, if it is 50%, then it will be 10 by 100. If I calculate ideal number of stages for a particular column, and the tray efficiency 0.5 this, and if tray efficiency let's take 0.4, okay, then it will be 25. So it depends on the what is the tray efficiency. So tray efficiency is very important parameter, and we need to calculate this one. Okay, and generally it will come from the industry, from industrial knowledge. So but there are three type of tray efficiency. One is point efficiency. Okay. Point efficiency means, let's say particular tray, okay, is there, nth tray. So yn is coming here and n is going out. So for a particular point in a tray, in each point, that is the local efficiency, that point efficiency, what is yn is going and yn what is coming, that composition, minus, if instead of yn, if it is in equilibrium, what is xn is coming, that equilibrium, yn star minus yn minus o local. So this will be your point efficiency. But if you see, if this what yn local, it is going actual, it is actual, if it is a equilibrium with xn, means then it will be yn star, then my efficiency will be 100% efficient. But whatever yn is going, it is not the, generally it is not equilibrium with the xn what is coming down here. So accordingly it is a point efficiency. I mean, in a tray, generally if you see, you can understand, if diameter is 10 meter of a particular separation column, which is very common in big industry. So 10-meter diameter means each point, there will be some difference, because some point liquid gas will be very good mixture, sometime it will liquid gas will bypass, some there will be some difference. So this is the actual efficiency for a particular tray, but point wise. Okay, so this is the one, is that is the tray point efficiency. Okay, now second thing is Murphy efficiency. So what is Murphy efficiency? Instead of point efficiency, if we consider the, if within this tray the all points have a similar efficiency, okay, same efficiency. So if I make that, what I will, if I can calculate the point efficiency and if I can make it average, then that will be the Murphy efficiency. Okay, so how Murphy efficiency is coming? Murphy efficiency, why? That is same thing. Instead of local, it will take the over the plate. Okay, whatever the yn going and yn plus 1, what is coming from the bottom, minus this star. So Murphy efficiency means tray efficiency. Okay, that is means, if we assume that whole tray is behaving like a similar, and how it will come, if I make the average of the point efficiency, then Murphy efficiency will come. But then there is another efficiency, that is called overall tray efficiency. What is overall tray efficiency? An overall tray efficiency, or a overall column efficiency in a section of the column, is sometimes used to determine the number of real strays. It is defined as number of ideal strays by number of real strays. You understand? So if I calculate the number of ideal strays from theory for a particular separation, okay, and when you will do it, really how many trays are required, then it will be that ratio. Generally, real number of trays will be higher, and then accordingly I will calculate the overall efficiency, and overall efficiency you will get from the industry data. And because people are doing all these things, and people have some experience that what are the different tray efficiency from their industrial knowledge, and they put that typical values. So you understand, as a chemical engineer, if you don't have the industry experience, so you can calculate this up to the ideal, but what will be the thing, that data you have to take from the industry, and generally it has been seen that typically 0.4 to 0.6 is the typical range of a tray efficiency. So that's why you have to calculate. So there are three efficiencies. One is point efficiency, Murphy efficiency, and overall efficiency. Some calculations are there, but it is not required much. Only you can understand the concept. This is the thing. And how will you calculate the number of trays, okay, for a plate column or plate tower? You have to calculate the minimum liquid flow rate for absorption. Then you calculate actual will be 1.222 times higher than the minimum. Then calculate the operating line, then make the triangle number of trays, or you can use the Kremser equation to get the number of trays. Okay, then for a particular column, that whatever number of trays you will get, that is the ideal number of trays. Okay, then you have to know the efficiency for this. Actually, overall efficiency is very important. If this value, you get this value from the industry, if you have some knowledge, then you use this one. So let's use this thing. So number of ideal trays by number of ideal trays by efficiency. Let's take 10 is number of ideal trays and efficiency 0.5. So 20 will be your actual trays. So 20 into, if it is 1 meter, 20 meter. So that will be your height. So you know that. So that's the thing we are going to learn here. Okay, so this is the last lecture of our absorption. Now I will share you this tutorial for this an assignment, and we'll conduct one quiz on two chapters, chapter 5 and chapter 6. Thank you and have a nice time. Bye.